Okay, so what I want to do is kind of just a bit of a dev stream, I guess. So we've got this is a building on the system called integrity layer, and the kind of intention here is to sort of write a bit of maybe like EDR logic, something like that. So the system called integrity layer allows us to sort of, I guess, intercept system calls as they're dispatching. And of course, whilst an EDR might want to just kind of log this activity, we can take it a step further, being a bit of an invasive EDR when bad things are happening, and we can demonstrate this quite easily, probably with some shellcode injection. So I think what we'll start with is we can just write a very quick, simple shellcode injector, and then we'll sort of be able to detect some bad bytes, some bad patterns, like you might see maybe from like Yara rules, something like that. Sort of custom EDR rules which look for known patterns of bad sequences. So what I have is some shellcode for opening calc. I've just nicked it off Stack Overflow. So what I'm going to do very quickly, I would zoom this in as well, which I guess we can do, but I find it difficult to code when I do so. So hopefully the resolution's okay. So we can set a constant buffer for the shellcode. So we can just do const shellcode, and we'll do this as a reference to a slice of bytes, and we will just paste in those bytes. Now, of course, we're just going to have to tidy this up ever so slightly. So let's get rid of these. Get rid of these, and we'll just do a quick find and replace on the backslash. So we want to do like I guess like a comma space backslash 0. So that should give us a nicely formatted. Wait, no, that's not right. We want to do where do we want the space? I think like that. Yes, okay, that's fine. So we just want to get rid of these, and I guess that should be oxdv. And then we just need a comma at the end of these. Oh, that's annoying. And a comma there, and that should be good. Awesome. So we have the shellcode, so we're going to write just a process self-injector, and we can probably in the EDR component, so we'll have to write a little bit of the driver and a little bit of the user mode application, but essentially we can scan for a pattern of bytes. So if it starts with these bytes, then we can say this is a known sequence of malicious shellcode. So the first thing we want to do, I'll tell you what, let's get rid of these because we don't need them, and we'll maybe just write a new function and we'll call it inject shellcode. So there's kind of always a sequence of things that happens when doing shellcode injection. The first is to kind of optionally open a process. So we can do that for our current process. The next is to allocate virtual memory. Then we've got write virtual memory, and then we have something like create thread, or you could perhaps like do an inline assembly jump on the current thread. You might come into sort of some stack alignment issues with that, possibly. I'm not sure. You could do like a naked assembly type function that would kind of unconditionally jump to the write address, so the allocated address. That's an option, but I think we'll keep it simple. So I am curious to do the naked assembly stuff, but I think we'll keep it simple and stick with create thread. So I might have to import a couple of bits and bobs into the toml as we go, but let's see where we get. So we'll start off by opening the current process, which is nice and simple. So we'll just say h process equals, and I'm kind of going to do what you should not do in Rust, which is do everything unsafe, just because it's a little bit easier for us. So we can say let h process equals get current process. So we're going to assume that that succeeded. We're not going to check for errors. So the next thing we want to do then is allocate some virtual memory. So we can do let, is this going to give us a pointer? I think it is. So palloc. We can say allocate virtual. Okay, so I just need to grab the crate for that. And we're just on the normal Windows crate. So I'm just searching for the function in sorry, it's virtual alloc, isn't it? Not allocate virtual memory. That's the NT version. So let's just add that in. So you can get that from the docs for the Rust crate. So we'll go with, hopefully, we'll just give that a second to scan in. Rust Analyzer is just doing its thing. It does take a second. Oh man, it's taking its time. I'll tell you what, whilst we're waiting, we'll probably add, I think it's Win32 security we're going to need for something else. And there's one more that we'll need security. I think it's for, is it create thread? I think it's like debugging. No, maybe it's write process memory. Yeah. So we'll grab this as well whilst we're setting things up. Might as well. So we've imported those, but we should have virtual alloc now. Oh, Rust Analyzer's having a paddy about something. Okay. So we'll call virtual alloc. So the I'm just going to get the docs up actually because I forget. I think this is asking for like an address preference. If we have like an allocation preference. Yeah, so we don't need to care about that. So the next argument is the size. So what is the size of the allocation? Well, that's the length of the shellcode. So we can take the shellcode and just call len. So that's going to give us the count of bytes that shellcode that the buffer relates to. Allocation type. This is going to be mem commit and mem reserve. And then we'll set the protection flags. We'll just go crazy and we'll go page execute read write. We don't need to concern ourselves with evasion for this, I don't think. So just for good practice, just because that could fail. So if it's null, then we will panic. I cannot type today, and we'll say allocation fails. Cool. So next we need to write the shellcode to the virtual memory. So we can do that nice and simple with write process memory. I always forget. Write process memory. I shouldn't do. Use it often enough. So the handle to the process, we're just going to pass in h process. Of course, we should check that it's valid, but we're going to assume it is. The base address is going to be palloc. the buffer is going to be, so this is a pointer to like a void type, so that's just going to be the address of shellcode. So we can do shellcode dot as pointer. Now that's probably going to come out as a pointer to a U8, to a byte, so we can just cast that as a, so we'll say as stackconst U8 as stackconst C void, and that should cast nicely. And we'll have to import that as well. So the size again is the shellcode .len and number of bytes written. So we're going to need a output buffer here. So we don't really care about it, but we'll call it so let mute out buffer, and we'll set that to 0, and then we can just pass a mutable pointer to the buffer. Now something's wrong. I'm not sure. Oh, okay, it's semicolon. Okay. So we're going to call unwrap on this because it could fail. I'm not particularly bothered about passing errors. If we panic, we panic. So final step is to create the thread. So create thread. So we'll just drop these down to make it a little easier to read. So thread attributes, let's just grab the API for that in my other window. So this is the security attribute. So we don't want to set any of those. Stack size, we can just leave as the default. So the start address will come back to parameter. We don't want to pass one to the shellcode. So that's if you had a function that you were creating a thread on, you would want to, let's say you wanted to pass some kind of argument to it, some kind of structure that allows you to do that. Creation flags, we just want to use 0, but this is a type, so we want to do thread creation flags 0. So that just instructs the thread to start immediately. And this is an output buffer to a thread ID, which we don't care about, so we'll just select none. So this LP start address, if we have a look at the prototype, we will see that it wants this LP thread start routine. So this is like a this is kind of like a definition that we need to define. So we're going to have to coerce the address in which we allocated the memory to that type. That's nice and easy. We can use the transmute function to do that. So we can just say let f pointer, or yeah, we'll call it f pointer. It's not really a function pointer, but we'll pretend equals transmute. And the source address is what we're transmuting from. So in this case, it's palloc. And what we want to do now in the turbofish syntax is we want to pass the type in which we wish to reinterpret that pointer as, and it is that kind of unsafe external system function LP thread parameter, which is a pointer to a C void. So what we can do now is we should be able to pass this in the sum enum, and it's going to tell us that we could have an error, but I'm not bothered about an error, so we'll call unwrap. So that gets rid of that. Now this on its own, I'm not going to run this actually. I'm not brave enough to take shellcode off the internet and run it. You know, bad things can happen. So we don't really need to run it to prove the point here. We'll run it in the VM. But you know, this kind of sequence of things will lead to shellcode running. So nice and simple. So we'll maybe take ourselves to the, let's look at the driver. So if we go back to the test program, the thing we need to, you know, as an EDR, the thing we want to concern ourselves with is when this memory is written, or when these bytes are written to memory. So we need to ask ourselves, well, what's a good time to intercept that? for me, the best place is going to be obviously write process memory. Optionally, if this was a really noisy API in the operating system, which, maybe it is, I'm not sure. Maybe create thread is a better API to hook, just in terms of trying to minimize disruption to a system. I suppose EDRs probably don't want to cause too much of a disruption. So for this, we're going to use write process memory because it's easier, I think. More so because I've already got the constants defined. So if we go to the driver, we should have the constant, let's see, unless it's in a shared crate, which it could be. So we have the constant here for the system service number, which is like the kind of like an index into the system service dispatch table. We have that constant defined here for NT write virtual memory. So you can see here it's hex 3A. So what this is doing here is whenever we get a system call, we've kind of inserted ourselves right into the throes, into the heart of that process of system calls dispatching. And what will happen is we will match on whatever the system service number is of the syscall. If it matches one of the ones we're monitoring, so NT open process, NT allocate virtual memory, NT write virtual memory, NT create thread, then we have the opportunity here to bubble this up to user mode as per kind of the previous demonstration as to how the system call integrity layer is designed to work. So what we can do is we probably want to match on, so we've already handled if it's open process, then we want to send the process ID up to the caller. So what we want to do now is we want to send the we want to send the buffer. We either want to send the buffer to user mode, or we want to pass the pointer to the buffer and the length, which is probably easier. It's a smaller copy. We don't really want to be doing large mem copies in memory. So let's just let's thrash this out. So let's say else if SSN is equal to SSN NT write virtual memory, then we want to so what we want to do is we want to return the values that we care about. So because of the expressiveness of Rust's enums, what we can do is we can kind of put data in here. The easiest way to do that is probably to define a type, just to keep it clean. So we can say pub type. This is where am I here? Is this a shared library? Yes, it is. I just wanted to check that this was shared between all the crates, so we don't have to duplicate work. So we can say pub type nt write vm inner, something like that, and we can set that equal to a tuple, and we want the address of the allocation, and we want the size of the allocation, and we probably want the PID. We probably want the PID of the allocation as well. To make this simpler, just because I'm doing this live, I think we'll leave it with those two, and we do pass the PID up to the user mode application. So we'll leave it at that for now, and we'll just write some comments to say inner type for nt write virtual memory, and we have the positional arguments of a pointer to the allocation and the size of allocation. Cool. So what we can do now is we can basically put this as the let's import that. We can add this to here like so. So now when we return NT-write virtual memory and we do anything with NT-write virtual memory, it's going to have some kind of invariant inside. So we're going to have to deal with this here. And I mean, this is the other beautiful thing about Rust. I'm not going to turn this into a Rust loving session. But one change like this, you are forced to handle all over your code. So, you know, it's probably quite easy in other languages to make very subtle adjustments to types and variations of enums or whatever, and perhaps not be forced to handle all circumstances of that change. So let's see. So for this, we essentially, this is kind of like a helper function to turn a system service number into a type. We don't really care about what's in here for the purposes of this. It's probably not the cleanest code to do it like this, but we will just provide a null, mut, or mute, and 0. And that might want to be in like that. So that is satisfied. So we'll go back to alt syscalls. So let's see. So in fact, let's get the docs up for NT-write virtual memory. So let's see what we have. So the first ag is process handle, so that's going to be an RCX. RDX, so the second argument is the base address, which is the base address of the process. R9 is the pointer to the buffer that contains the data to be written, and then R10 is the number of bytes to write. So we can take ags 3 and 4, which is the number of, the pointer to the buffer and the number of bytes to write, and we can send those up to the user, nice and simple. So we can say let p buff equals k-trap frame dot what's k-trap frame? Is that gonna work? Just for now, we'll return this to make sure we get proper IntelliSense. Yeah, okay, that's fine. So R9 is the pointer to the buffer, and let size equals k-trap frame dot R10. Now we don't have IntelliSense on these, so something is potentially wrong. This could be Rust Analyzer. So let's type this correctly. So we'll say as star const c void. So that's going to be that's going to be the I'm just considering whether we're dealing with like a double pointer here, but I don't think we are. And I think this can be cast as a usize because the type is a size t in the NT-write virtual memory prototype. So this should be fine. I mean, we'll soon find out. We could probably do a debug print actually. So we'll say skill info NT-write virtual memory, and we'll say pbuff is this. And we can say size of buff is this. So let's just pass those in. So we have pbuff and we have size. Okay, so now what we can do, instead of returning just this, which is kind of the bland NT function, we're just recasting them here or retyping them with the correct invariants. So we can return instead nt function, nt write virtual memory, and then it's the tuple with the pointer to the buffer and the size. Cool. And I'm going to add that to the spell check because that is annoying. And I think that's all we actually need to do for the driver, here. Rust Analyzer is definitely broken for this at the moment. I'm not sure why. It can be annoying writing drivers actually in Rust and VS Code for this reason. But alas, we get by because Rust is just so much nicer than being forced to write C. So let's now go to the EDR's user mode component. So as we demonstrated last time, we do deal with the NT-open process case. So just for context, I suppose this is kind of the core loop where the EDR is checking for events, like system call events that have been bubbled up from the kernel or from the driver. So this is us dealing as the EDR with NT-open process. So let's take ourselves now to capture NT function and then NT write virtual memory. And the two arguments we have, of course, are the pointer to the buffer and the size. And these, again, probably want that syntax. So what we can do in user mode is we can print... in fact, I'm just going to get rid of some of these prints as well, just to reduce the noise. So we can print received event for NT write virtual memory. We have p buff is going to be that. So p underscore buff, and we have size is size, like so. Cool. So when we get the information out of the driver or out of the ioctl, some of the information we get is the PID. So let's just make a quick copy of that, or however the compiler wants to do it. So let PID equals taken dot out dot PID. So we're going to now have to open that process. So we can say let h process equals open process. I don't know if we're in unsafe here. I'm sure it'll tell us if we're not. So open process, and desired access will go process hold access. Inherit handle is false, and the process ID is PID. So let's do let OK equals open process, else we will print a line that says could not open process, and we will print the error code in hex. We'll just do get last error, like so. And we will want to... Can we break? I don't think we can break out of a... Oh! Okay, maybe we can. So that break then I guess will take us out of the match and allow us to just complete the syscall anyway, because we obviously don't want to interrupt the process, because that'd be annoying to deal with. So we have a handle to the process in the happy path. So the next thing we want to do then is we want to read that virtual memory. So we can say, let's think. Will we have to copy that into our own buffer, or can we get a window? Let's have a look. Read virtual memory. Or probably read virtual memory X or read process memory X or something. Read process memory. So a handle to the process, the base address, a buffer in a size. I'm just trying to think, can we... No, I don't think we'll be able to cross the process boundary. So we'll make a buffer. So we'll do this as a vector. So we'll say let buff, that'll have to be mutable. So let mute buff equals vec, and we'll do with capacity, because we know the size, because it's here. So we can say with capacity size, and that's going to be a vec of U8s, so a vec of bytes, and we can use the turbofish syntax there. So let's say we'll probably handle the error for this as well, because I think we want to be more careful in the EDR application. So we'll just say let result equals read process. Okay, I'm going to have to grab the correct module for that. Although I think we have it already. Let's see. Oh no, of course, because we did it for the injector, didn't we? We didn't add it for this, so that is fine. So I'm just going to give Rust Analyzer a second. Although I think it's finished actually. So let's go read process memory. Perfect. So let's just drop these down like so. So handle to the process is hprocess. Base address is pbuff. So this is what we got from the driver. Long pointer to our buffer, so we can probably just do buff.as mute pointer. And it wants that cast as a might be able to just do that, yeah. So we can cast that to a mutable C void, which is just a void pointer. Size is the let's see, that's just going to be the size of the bytes to read, so that can be sed. Number of bytes to read, so that's an out buffer. So I suspect we can we pass a none? We can, so we don't care about that. Again, in the real world, you probably would do. But for the purpose of this, I do not. So, in fact, rather than defining that, we'll just say if let error e, if it gives us any, yeah, it does. It gives us an error. So we can say println error reading process memory of PID. Let's pass the PID in, and we will give the error. Like so. We'll print it with debug mode, and we'll do the break to take us out of the match. Cool. So at this point, we should have read the memory into the buffer, and this next step really is as simple as trying to pattern match, pattern match kind of known bad bytes. So we could, let's make this really simple. In the real world, you want to do this more in a more complex manner than kind of this arbitrary. Take the first few bytes, and if it matches, it's bad. This is, of course, just for demo purposes. So let's just go back into the test binary, and let's take the first line of shellcode here. So we can say if buff dot starts with. And then it wants a slice of U8s, a slice of bytes. So we can just do that nice and simply like so. So if the buffer starts with that sequence of bytes, then we can say println malware detected, suspending process, something like that. And what we can do at this point is we do have the option to send this syscall allowed as no. I don't want to do that now because I expect if we pass no down into the alt syscall part of the driver, and we quickly edit this to prevent that syscall from dispatching, will probably cause a blue screen without me having a close look at it in slow time. So rather than do that, we will just enter a loop. So this is just going to stop the syscall from dispatching, and you'll actually see the process hang. So not necessarily this process. In fact, we should probably add a sleep, just to, I say not burn out the CPU. I don't know if that's a thing anymore. I'm fairly sure the scheduler can probably take it, but I think historically I've always been told, at least, that it's good practice to at least sleep the CPU for a very short amount of time. Anyway, so that should work. The error in here is just a Rust analyzer problem, so we'll ignore. I think we're probably ready to build. The one last thing I'll do here is let's add some prints. So we'll say print line current process handle, and then we'll just do something like this. So we'll say h_process. Allocate memory. So let's do print line allocation of shellcode memory. Of course, that hasn't written the memory, that's just the allocation, is p_alloc. And let's just copy paste that. And so this is after write process memory. We can say process memory written to buffer, and sure, we can keep the pointer. Now I'm not going to create the thread just in case this goes wrong. Again, I don't really want to execute arbitrary shellcode on my machine, even in a VM. So we'll just simulate. So we'll print thread started, and we will loop. And again, we will sleep, just for brevity. Okay. So I'm going to go and build those, and then we'll run them on the VM and test them, see what happens. Okay, so let's bring those binaries over. So delete the old engine, and I'll just copy the new one. Likewise for the test binary. Let's bring that over too. And we also need the driver, so let me just grab that from the debug directory. So skilldriver.sys. Cool. So let's open. I've not got WinDebug open, so hopefully we don't get a blue screen, because this VM takes, I swear to God, like 10 minutes to start up for some strange reason. So let's open debug view wherever you are. And we're going to want 2 admin terminals. And let's just cd into this directory here. So I think we'll run the shellcode in a standard process. So let's start the driver. So that was successful. We'll start the engine. So let's do that here. So we'll do skill underscore engine.exe. So that's going to start the engine ticking over, waiting for those ioctls to pop up. And if you watched the last video, those are the dangling fishing lines. Terrible simile. Is that the word? So let's grab the. What else do we need? Okay, just the test binary actually. So let's see what happens if we run skill underscore test. Fingers crossed we don't get any horrendous blue screens. Let's maybe, let's maybe give ourselves a little bit of space to print some stuff out here. Let's go. Okay. Let's see. So received event for NT write virtual memory. Oof, that's not a correct pointer. And that's also not a correct size. So we have an error somewhere. So let's jump back to the code and see what the problem is, shall we? Okay, so I guess the thing that has gone in our favour is it has suspended the process. It never completed the syscall, so that does show that the skill kind of method works. So let's just stop the driver. And let's kind of have a think. Let's reason about what might have happened here. So the pointer to the buffer is 70. I'm wondering whether these are the wrong way round. Could the size be hex 70? Or even not hex? What's hex? Hex 70 is 112. Okay. Let's have a look at the shellcode. Is it going to tell me the length? Probably not. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So let's just do 16 times 1, 2, 3, 4, 5, 6, 7. So 16 times by 7 is 112, which, was that not hex 70, 112? Yeah, okay, so I think we've got those addresses the wrong way around. I think this is probably the address just as like a decimal number. So let's swap those around in... Who was at fault? Was it the driver? So the pointer to the buffer is R9. Oh, shoot. I know what I've done. That was supposed to be R8 and that was supposed to be R9. My mistake, guys. My mistake. So let's... I'm just going to quickly rebuild the driver. That will take a second. The user mode app and the kind of the test malware binary or whatever, they're fine to remain as is. So that's built. So let's grab the VM and let's clear all of this. We can get rid of that. Clear that out. And same for this. So let's delete the driver. Bring the new one over. And let's go and start the driver. Let's clear that out and run the engine. Cool. So the next thing we want to do then, as before, is the shellcode. So let's do what was it, skill test. So let's see. Fingers crossed, guys. Pray for me. Okay. So we did get that buffer. Is that the same address? No, it's not, because what are we printing? Pointer to the buffer. Are we reading the address as... I mean, that's not a kernel address. is that that's the address of the buffer though, as opposed to the address of the memory allocation, which is fine, I think, because I think what we've got is the address of the shellcode, and I mean let's verify that. So I think I have x64 debug. So let's just attach ourselves to skill test. And let's just go to the dump. Let's have a look for. We don't want that. So it makes sense, right? We've looked at the. This is the address of the buffer. If you think about the arguments in NT-allocate virtual memory, we don't want the address of the buffer. We want 31 db64. Let's just go and have a look. 31 db64, yeah. So it's the address of shellcode, so of course that makes sense. But we never matched on that pattern of bytes, did we? So I'm fairly sure we said if the code starts with this sequence of bytes, then we want to stop it, but we never got that print. So what went wrong in the engine? So we've got the pointer to the buffer, we've got the size. We never received an error from reading the memory, but I know what's happened. This is like a little Rust idiom when dealing with raw memory like this. So we've allocated the vector with a capacity. So a vector is like a fat pointer, so it contains a pointer to the data. It contains the capacity, which is how many elements it can have without it needing to go back to the allocator to resize. And it contains the size, or I think the length it's called, which is how many elements exist in the vector. So because we've kind of done it in this, well, I was going to say verbose way, we haven't done it in a verbose way, we've just written it to the vector, but a vector is it's a managed kind of like a smart, is it a smart pointer? I don't think I'd call it a smart pointer, but it's a managed piece of memory. We just need to set the length on that, so we can do buff dot set len, and we want to set the length to the size we read. So this is actually probably where we would. I know I said before we don't care about the size read, but let's be safe, and let's call it out size, and we'll just pass a pointer to the out size in here, like so. And then we can set that to the length of out size. So let's rebuild this. Third time lucky, but I mean this is kind of what it's all about. This is the joy of low-level programming. So let's clear these bad boys. Let's stop the driver, and we'll just start from clean. So I'll just grab the binary from the engine. Okay, so let's drop that here. Cool. So let's, we don't need two windows there. Let's do that again. So let's start the driver. Let's run the new updated engine. And let's see what happens. Hey, there we go. So it has now detected that malware, and the EDR can respond as it sees fit. I reckon that's probably enough. I don't know how long this has gone on for. Maybe about an hour, maybe about 40 minutes. So we'll call it there. If there's anything you do want to see, if there's any kind of coding content, or Rust content, or driver content, or security content, whatever, please let me know, because I do kind of want to probably do a bit more streaming like this, or make some content that people would find helpful and useful. Most of this is a hobby for me, so I enjoy doing it, but it would be nice to do something which the community would kind of benefit from. So let me know, and I'll catch you next time.